All right, let's work 5.77. This is a conceptual problem. In this problem, you're given two data plots on the same graph, okay? And these two curves are supposed to show data for helium and argon. Now, if we study the curves very closely, what we see plotted here is it's an XY plot. The y-axis is the relative number of molecules that are exhibiting a particular molecular speed, and the x-axis is the molecular speed or velocity. So this axis is basically a measure of how fast the gas molecules are moving. You might measure that in meters per second, something like that. Okay, now obviously the molecules, or atoms in this case, are constantly bumping into one another, so they're changing direction. So this is not necessarily the velocity in one direction. But it is a measurement of molecular speed. And this axis basically tells us, what fraction of atoms have particular molecular speed. So there's two data series plotted here, number 1 and number 2. I think they're in different colors in the book, but I've made this one a solid line and this one a dotted line to differentiate between the two, okay? And what you can see that's highlighted here between data series 1 and data series 2 is data series 1 has a relatively compressed distribution at lower molecular speeds, and more or a larger fraction of the molecules have particular speed within this narrower window. Whereas for data series number 2, we have a little bit more spread of a data, and also that sort of maximum or mean or median, if you will, is at a much higher molecular speed for data series 2 than it is for number 1. Okay, that mean or that median somewhere in here for 1, whereas for data series 2 it's way over here, much higher molecular speed. Okay, so that might give us some hints to help us answer this question here in a second, or the series of questions. So we're told that, again, these curves represent helium and argon, and also one thing I didn't write here that's important. Both of these gas samples are held at exactly the same temperature. Okay, so both the gases are at the same temperature. That's also important for this as well. Because if you change the temperature, you shift this distribution left or right for any gas. Okay. So then they're asking us a series of questions. Some of these I actually made up just to sort of talk about this with you. Okay. So which curve represents argon? Curve 1 or curve 2? And how do we know which curve represents helium? How do we know? Okay. Well, what do we know about these two gases? Okay. Well, one, helium and argon are both considered inert gases, right? They're both in that last column on the periodic table. But the thing is, helium is at the top of that table, has a molar mass about 4 grams per mole. Argon is third in the table. Its molar mass is approximately 40 grams per mole. It's a shade under that, but we'll say 40, okay? So the thing is that argon has a molar mass about 10 times greater than helium. And that's important, okay? Because remember, when we treat these guys as ideal gases, both of these particles are in motion at some velocity. The particles have some mass. Now, when the atoms, in this case, collide with the walls of the container, they exert a pressure. They do that by collision, of course. They transfer some of their momentum to the walls of the container, which makes a pressure, okay? So the speed is important for the momentum, but the mass is also important for the momentum, because any given collision, you basically want to transfer essentially similar energy over, if you integrate the collisions over time. So what does that mean then for this plot? Well, based on the fact that helium is so much lighter than argon, I would fully expect that helium is going to be moving much, much more rapidly than argon. So number 2 probably represents helium, and number 1, with the lower average velocity, it's going to represent my more massive argon, okay? So that helps us with A and B here. Now C, which of these gases is going to effuse more rapidly or more slowly? Now remember, this effusion business basically means the leaking of a gas from a container through a very small hole. The model for that relies upon the gas atoms or molecules basically, I won't use the word diffusing, but colliding with the surface area of the hole such that they're removed from the container, okay? The rate at which that occurs is directly proportional to the velocity of the gas. The velocity is what's important. Higher velocity, higher rates of effusion, okay? So the thing is because helium has so much higher velocity, I would fully expect helium to effuse from a very small pinhole much more rapidly than the argon because its molecular speed is much higher. So argon will effuse slower, helium will effuse more rapidly. Lastly, we're asked to draw a comparison with fluorine gas. Now remember, fluorine gas is a diatomic, right? It's one of our halogens. F2 gas is what we're talking about. If I want to report the molar mass of fluorine, it would be 2 times 19, 19 being the number on the periodic table, which gives me about 38 grams per mole. That's the molar mass. I'm doing this because I want to compare that molar mass with one of my test gases to see which one's more like, because that mass is what's crucial here. Now, clearly, 38 is pretty darn close to 40. So as a result, I would expect fluorine gas to exhibit behavior that's somewhat similar to argon in terms of its molecular speed distribution at this particular temperature, and also with respect to its effusion behavior. It's a little bit lighter, so maybe it effuses a little bit faster than argon, and maybe there's a little bit of shift towards the right here. But if I'm going to compare which gas, which of these two gases does fluorine behave most like, I'd be forced to say argon for sure.